Finis Southworth, thank you so much for joining me here.
Oh, my pleasure, Bret. That's great.
So you were the former CTO of Areva, one of the legendary giant nuclear companies.
That's true, yeah.
But before we get to that, I want to just walk through your whole history. I know you you were teaching at University of Illinois nuclear engineering for a while.
Yep, in Urbana-Champaign.
Were you always interested in nuclear? How did you get started there?
Oh, God. Well, I finished my PhD at Florida in '74, and then sort of, yeah, exactly. So they were looking in Illinois, and I really wasn't thinking of going to teach. I was thinking of going to a lab. Yeah. But when I interviewed there, I decided to interview, and it looked very interesting, and it matched what my doctoral work had been on in fusion. So they were looking for expanding their fusion research program. Cool. So, and Illinois is a good high reputation school, so I went.
And why fusion?
Well, it's out there, so it's like a soap opera, as I put it. From the days I worked on fusion, either my doctorate or in the at University of Illinois, the 3 years I was there, the progress in the various concepts is like a soap opera. You can tune out for 5 years, come back in, it's the next day, and so you really don't miss anything by being out 5 years. So that's not why I was in fusion. I was hoping that it would make a difference, but it, I think reality took over at some point, and it was, that it was a fond hope, but it was clear from the work we were doing even that it's not going to be a practical energy source for a long, long time. And so I left in '77 and went to Florida Power and Light and their nuclear program, which was for them nascent in that they had 2 operating reactors, but they really had taken no responsibility for it.
What does that mean, they took no responsibility for it?
Well, they had bought it as a turnkey plant, the Turkey Point units. Even the fuel was leased. So, and the price for the fuel for Turkey Point in the contract was $1 per barrel. That was the contracted price. So they had to convert that to what does that mean in BTUs and so on. But Westinghouse would own the fuel. You would use it, and they would control the core fuel management. And at the end of the fuel cycle, you would put the spent fuel into the pool for 5 years, and then they would take it away. And they would recycle it or whatever they wanted to do with it. So that was a complete end-to-end contract with Westinghouse. Of course, by the time the plant started up, they defaulted on all of that.
What does it mean? That they defaulted on?
Well, that they wouldn't agree to the $1 a barrel anymore. That was predicated on a $6 a pound uranium price and a $38 per SWU enrichment price. And of course, both of those changed dramatically by the time the plant started up. So they defaulted and said, well, you're going to have to pay for the actual uranium price and all that. So, and then they said, well, given the trend in the government, that you probably weren't going to have commercial reprocessing. They had the West Valley facility started up, but it was, a pilot scale. So they wouldn't be taking the fuel away and recycling it either. You have to hang on to your own fuel.
So that's interesting. So at the time, there was this assumption that there was going to be reprocessing in the U.S.
Oh yeah, absolutely. Yeah, that was the whole predicate. Was they would take it back, reprocess it, refabricate it into new fuel with their various customers. So all of that fell by the wayside. So they said, well, we're out of the fuel business. We'll fabricate it for you for a price, but you have to manage the whole nuclear fuel. So they really hired me to come down and set up, well, how do we do that? Do we buy uranium? Do we buy enriching? What do we do with the spent fuel sort of thing? And we were still thinking even then about having it recycled. I mean, the Allied General was still going strong. It wasn't until the April '78 speech by President Carter where he basically stopped all reprocessing. And so the Allied General stopped in its tracks overnight. West Valley stopped, Milton, what was the General Electric one in Illinois? That one stopped. And he also basically outlawed commercial enrichment.
So, why? What was the mentality at that time that you'd want to take options off the table?
Yeah, well, Carter's logic was, and he ascribed it to his 10-year-old daughter, Amy, who thought the number one problem facing the nation was nuclear proliferation. So these are proliferation technologies, reprocessing and enrichment. So we're going to take them off the table for commercial industry.
And that logic, though, I mean, just doesn't hold up to me. You'd think, yeah, take it off the table for other countries elsewhere,
right,
where it could be used as a
right,
weapons factory.
Exactly.
But if it's your technology, if anything, that would give you an information edge if someone else started doing
right,
it somewhere else.
Well, in the industry, clearly, it wasn't a popular decision.
Right.
So it was, at the moment, in April '78, I sat there and watched that speech, and I was speechless. I thought it was the end of the industry, but over time, basically thought what that meant was, well, okay, Department of Energy will enrich. They'll provide the enriching out of Paducah or wherever, and we will, we'll negotiate market prices with them. We eventually negotiated that you could buy offshore enriching. So Eurodiff and Kojima became sources of enriching. I think we're allowed to take, this was like in '81, they added that option. We could take up to 25% of enrichment from offshore sources. So we did that, and that kept the Department of Energy honest in their cost of enriching. It did escalate a lot, went up to as high as $138 a kilogram SWU, I think.
Why did it go up over time?
It really never was all that inexpensive with the diffusion technology. It really,
right,
if you really looked at the cost of that facility, it never was as cheap as it.
So in early days, we had multiple strategies for enrichment, and this was for weapons material too.
Right.
One of the strategies was to do this gaseous process, where you'd separate the atoms by weight when they're in a gaseous form by pushing them through some membranes or something.
Right.
And the other more common way, and the way that proved to be much less expensive, is this centrifugal process.
Yeah, and they hadn't perfected centrifuges at that time. It wasn't until later that Urenco and others were able to perfect. I'll say perfect. There's, there maybe are better ones, but they work very well, and they're much more efficient and lower cost per SWU than diffusion will ever be. And
so when you say SWU, you mean separative work unit, which is some unit of measurement somewhere in the stack of enrichment.
To move a kilogram of uranium hexafluoride up to a next notch of enrichment. Yeah, so it never has been a particularly well understood term, I don't think. So now with the LES facility in Texas, and Areva almost built a facility in Idaho, as you probably know, the Eagle Rock facility. We were licensed for it, and we had the design for it. So we intended to build it, and it would have been about a 1/3 of the national use capacity. But when the Fukushima hit, the market collapsed. So because there's 50 reactors off the market overnight.
I see, the international market
collapsed.
Because there's a global fuel supply chain, and the ones that were shut down weren't in the U.S., but they were in Japan, and that's still represented.
Exactly. So that's more than 10% of the total. And with the new enrichment facilities in France and the one that we had in Texas, and still at the moment had Department of Energy, there was more than enough enriching. It wouldn't have been wise to spend the money to build that new facility in Idaho at that time.
Back to Florida Power and Light. How many nuclear power plants did they have at that point? Was it just Turkey Point? Or?
Well, just St. Lucie 1 was finished in '76, had some problems, and they fixed that by '77. So by the time I got there, they were just really starting up St. Lucie 1. And then in '78, decided to build St. Lucie 2, and October of '78. So as you know, 3 Mile Island was in March of '79, so 6 months later, we have 3 Mile Island, but we pushed through and started up in 58 months. So we went commercial in August of 1983.
Yeah, I've been digging through the data, and there's something, there's a lot of what I call mythologies in the nuclear space, things that the nuclear industry loves to talk about, whether they're conferences and all over the place. And one of these things is public sentiment and how we lost the social license after the various accidents, and how the country turned against against nuclear after 3 Mile Island, but the data isn't showing that to me. The data is showing that all these many construction sites were proceeding ahead right after 3 Mile Island.
Right.
And it was mostly economic forces more than anything that discontinued other projects.
Yeah, I think people forget what the late 70s and the early 80s were like. Bond interest rates were 14 to 15%. Inflation was 12 to 15%.
So that's what you're saying is that made it very difficult with the bond interest rates to borrow capital, large amounts of capital to build these intensive projects.
So, you're just looking at just the huge amount of capital. And if you get a slight delay when you have interest rates like that, it just spirals out of control. So all 4 units that Florida Power and Light built in Florida were finished in 5 years or under, 60 months or less. So never overran a schedule.
Why can't we do that now?
So every one was built on schedule or ahead, like St. Lucie 2, the last one was built actually with 3 Mile Island backfits occurring during its construction. And we still built it on budget and ahead of schedule.
Why can't that be done now?
I think, well,
these
there's a number of...
too. These were like 800 megawatt units.
Oh yeah, 800, about 900 megawatts. Yeah, so they're big units at the time. And so you had Comanche Peak and ANO2 and a whole variety of other units going on at the same time. And most of them were starting to have delay after delay. The license number for St. Lucie 2 is 104, 50-104. It was the 78th plant licensed. So from the time it got its construction permit, it passed 25 units by the time it started up. So one of the constant battles up in Bethesda at the time with the NRC was to constantly encourage them, no, we're not slipping. You have to keep that chapter on track because we're going to meet that schedule. And so the project manager up there would drive the people, okay, well, you better switch over to this FPL review because we don't want to be the ones holding them up. So we did that. It was a constant battle for the entire 5 years. But we had 30 people in Bethesda in an office space across the street from the Phillips building in Bethesda. And they were, every workday, they were over there talking to the reviewers.
So what you're saying is knowing that certain regulatory communications could lead to potential delays, you proactively sent Florida utility employees to permanently work out of Rockville, Maryland, right across the street.
Right across the street. Well, it was Bethesda then, but it was, but it was, we would have done it at Rockville if they were up at White Flint at the time.
So is that done today at the sites in?
I don't know how much it's done today. Yeah. I mean, all we've got at the moment is Vogel, but so I don't know what presence Southern has up there, but I know they have some, Amir Afzali and others who are up in Washington, but I don't know how much they walk the halls.
Yeah, it seems like this is an essential project management skill to have to get the people up there and make sure they're on track no matter what.
Well, there's a variety of things, I think, but it's, in 1983, there was a big IEA study published, a conference held for a week in Vienna, and it was on nuclear plant construction successes. And of course, St. Lucie 2 was one of the big ones. Or it was 83 or 85. It was 85. And so the project manager from St. Lucie 2, Bill Derrickson, presented at that conference, and it had a very lengthy paper. And so he has a chapter in that report, and he talks about, why do we think we succeeded at this? It was one of the most difficult times to license and construct. And I think, to me, I'd put a lot of it on the project manager. The project manager has got to have the authority and the will to see it through. And when Bill Derrickson was tapped to lead the project, he was in the project management department at Florida Power and Light before that and had worked on the other 3 nuclear units, but he'd never been the head of it. So he says, well, I'll step out from my regular job and do that, but here's what I need, he says. And he put some pretty strong restrictions on it. He says, for one thing, I have to report to the board of directors directly, not to the CEO.
Whoa.
I want as much sway as the CEO has so that I'm not waiting for management decisions in Florida Power and Light. I have as much control. Otherwise, I'll have staffing holdups or whatever, and I can't have that and succeed. So that was one of them, and he had others, but it was him directly reporting to the board. I thought was one of the keys.
Amazing.
And he says, this is a company buster if you don't succeed. So if it starts dragging on, this could bankrupt the company. So you have to do better than that. So and he'd done very well in his roles on the other plants. He was assistant project manager on the St. Lucie 1, which came in on time, other than the operating problem right at the beginning. And he'd even, like I said, the Turkey Point was a turnkey plant by Bechtel and Westinghouse. So Bechtel really drove the construction, and very little Florida Power & Light did to influence it. But I think Bill Derrickson learned a lot from observing it. But so another one was, a year in advance of the construction, he froze design. He says, okay, we've had this long period of jawboning and discussing, what will be the final design of this plant. It's frozen. Now the project team's going to work on optimizing the construction. Yeah. And they took a year to optimize the construction. And when they walked in, they were essentially 100% design complete. They didn't have any open issues or open supply chains. Well, I'm not sure we'll get that valve, but I'm sure we'll be able to solve it when we get there. Everything was decided before they started.
Amazing.
Yeah. So if you take Areva's Finland plant, the Olkiluoto, less than 10% final design complete. Almost 90% of the supply chain they really didn't know when they started.
But it's interesting because it's not like there hadn't been runaway cost, out of control nuclear power plants up until this latest batch. Financial troubles. You'd think the first thing that the CEO of the utility or whoever was building was,
what have we learned in the past?
That's exactly right.
And I can tell you, in the case of TVO and Areva Siemens, they didn't. And you're just going, what? So from the TVO viewpoint, it was back to, Areva Siemens committed to a fixed price turnkey contract. They're taking all the risk. Why would I care? I don't know if they're truthful or not, but it doesn't matter because my fixed costs are fixed. What they didn't learn was, when you look at the fixed cost plants in the US, which stopped in 1973, there was none after 73, it didn't matter. You could say it's fixed cost, but if it goes bad, utility's on the hook. I mean, the NSSS vendor, the constructor, the AE are all going to say, well, we're out of money, and we ain't doing any more until you help us fix this. That's what happens. That's what's happening at Vogtle, right? Yeah. So, I mean, they can't finish this without Southern saying, okay, I've got to step up. Because Westinghouse is going to say, well, in fact, we're bankrupt, so we can't do that.
It's interesting because that's a double-edged sword of the fixed fee model. And
it is.
I kind of like the fixed fee model. I think it properly aligns incentives, but you can't then have that issue come up later.
Yeah, I'm okay with fixed fee. I'm not okay with fixed costs. Okay.
Oh, interesting.
Right, because if you say I'm fixed fee, but cost floats, well, then you still don't want your cost to go way out of line. So the utility, the owner, is going to want to make sure that it goes well. Yeah. He has the incentive to see that through. And the vendor wants it to go because, if a $100 million fee on $5 billion is a lot better than a $100 million fee on $10 billion, because that's a lot more work with no more fees. So their last $5 billion is essentially without fee. Yeah. So it incentivizes them both to go in the right direction. That's one model. There's other ways with incentives that can line things up better, but a one-sided, you take all the risk, fixed cost, fixed schedule, and we'll just sit back and see how it goes. That never works. It has never worked in the nuclear business. They should get that out of their brains. That's a key one. So, yeah. And so I'd say that's one of the big advantages of St. Lucie 2. The project manager was Florida Power & Light. Yep. He drove the construction. He managed the entire construction. So, as opposed to some outside company managing it. So.
And what was your role at the time? You said you were coming in.
I was in fuel. Yep. So I came in to help with the fuel. So in '78, when we were launching the St. Lucie 2, I had one system as a responsibility, and that was the core. So but that's pretty trivial at that point. So, it's notional, and you're saying, do you want it to be able to do load follow? And we all said, no, we don't want load follow. It's a killer. Well, it eats margin to be able to load follow.
Right.
So the part length rods and that, they end up where the accidents have less margin, so you basically, restrict the operation more. But if you do away with load follow, you say, no, I'm going to stay hot, straight, and normal, I've got more margin, I've got more fuel economy and that sort of thing. So we all told them to take out the part length rods and don't put them in there and so on. But and we argued a lot about the form of the fuel. They wanted to go 16 by 16. St. Lucie 1 is 14 by 14 fuel. We wanted to stay with 14 by 14, mainly because St. Lucie 1 was 14 by 14. Mm-hmm. So let's keep everything identical if we can. And we lost that argument. We ended up going with 16 by 16.
Why? Why do you, it seems to me like that would have been, so by the way, when we say 14 by 14 or 16 by 16, what we're talking about is in an assembly,
right,
there are a certain amount of rods, length by width,
right,
and that's the number that we're referring to.
So obviously the 16 by 16, you have, instead of 196 fuel rod locations or potential locations for fuel, they have large holes that take up 20. So you really have 176 in the 14 by 14. In the 16 by 16 is 256 minus the 20 is 236. So you're going, oh gosh, so for the same power, I have all this extra fuel rod area. So I have 30% more margin to DMB. My linear heat rate is 30% lower. Oh, it's wonderful. So by the time the first 16 by 16 plant started up, which I think was San Onofre 2, was they determined they had a lot of rod bow in the flimsier rods, as opposed to the 14 by 14.
So less structural stability.
Less structural stability, and that ate up all of the DMB margin. It actually was a little worse. So, and then they found out that the way they manufactured them, they had higher axial growth, gave you less margin to the shoulder contact at the top of the fuel assembly. You don't want them to touch, because once they touch, then if they keep growing under irradiation, they'll flex, right? And then you close your channels, and that's not good. So, we went through all of that after the unit started up. They said, okay, well, you're going to have to take the whole core out and inspect all of the fuel for this rod bow due to axial growth at the end of the first cycle. They did that at ANO2. They did that at San Onofre. There were like 3-month outages to tear the fuel apart and look at it. So we said, okay, well, combustion engineering, here's what we're going to do. We're not doing that. We're not putting you in charge of this at all. We're going to go our own way.
Yeah. So
we got EPRI to help us, and we put together our own axial rod growth model and said, we'll validate it at end of cycle 1 by remote measurements. And we measured every fuel rod shoulder gap in the core. As it came out of the core to spent fuel pool, we ran this device. B&W made the device for us.
Babcock and Wilcox?
Yes, Babcock and Wilcox. We contracted them, the SPICE group or services group. Can you make us a device that does this? Oh yeah, absolutely. So we contracted them. They did it. We did the statistical analysis. We validated our model and submitted our report before the refuel. We never hit critical path. So St. Lucie 2 had a record first refueling, and we did this 100% inspection of fuel and validated our model and got the topical up to NRC before the outage was over. Wow. And we had alerted them and told them what we were doing, and so they were all on board. So they said, if the answer turns out the way you say, you'll be good. So off we went, and we never lost a day. So wow. Yeah, so it was the shortest outage for PWR up to that point. This was in late 84.
With all the additional work.
With all the additional work. So yeah.
Amazing.
So yeah, so that was fun.
So you became the guy probably known as who could manage anything, who could take on any challenge.
Yeah, that was pretty much it. Yeah.
And then where did that lead you to?
Well, Florida Power & Light won the Deming Prize in '89, and I was a key part of that. And traveled to Japan to benchmark plants over there. Kansai Electric in particular became our sister utility. So it's absolutely right what you just said. As I became known as the change agent, somebody who can make change in Florida Power & Light. And I felt like people that worked for me became more independent, more capable. What they really found out is just what they already knew. They just didn't speak up. They didn't feel empowered to speak up. With me, they quickly felt they were empowered. In fact, they better feel empowered, because don't ask me the question. It's your job to know the answer to that. What do you think we ought to do?
That's some good leadership, because that means that your efforts scale underneath
Yes, yes. So the organization improves.
Yeah.
And I led some change structure, Send Delaney and things like that in the with the whole plant in 86, 87. So one of probably the most tiring but satisfying parts of my career was right there.
Yeah.
But I was we got a new CEO in 89. Jim Broadhead took over from John Huderberg. And Huderberg was, I really truly enjoyed him. He was the one who got us into the whole Deming thing, and we won the Deming Prize in 89. And so as soon as we won the Deming Prize, I called the executive VP, the same one who drugged me over to operations, and says, it's time for me to come back. I've done my 60 years. And he says, okay, well, I've got a challenge that you should do anyway up here at corporate. So he brought me up for system planning. You know, let's get our capital expansion plans for the next 10 years, the 90s, in order, and let's get them approved by the Public Utility Commission. So I was put in charge of that, and it was just, geez, I have no idea what to do here, but I'll figure it out. And of course, we had a great system planning group. I mean, they planned the generation, the transmission, the distribution. You know, they do all of that with all of these software models and analysis, and really outstanding. And they modeled the whole state of Florida, and geographically, Florida Power and Light has 3/4 of the state, but so the Public Utility Commission just relied on us to do the whole state, and TECO and Florida Power Corp would use our results, you know, for their territories. But we had high trust with the Public Utility Commission. So when we filed that and set all the testimonies in and did that determination of need, it was all approved with some minor wrinkles about independent power producers, which were going to be coming up in a partially deregulated way. And so we had to incorporate that, which we did. But then it was, at that same time, we got this new CEO, and he was looking for, well, gosh, we got a $10 billion expansion plan for the 90s. Nobody could explain it to him well enough, so he stopped talking to the shareholder manager and said, came straight to me and said, you know, can you explain this to me? I said, sure. So he says, well, I understand that. Why didn't those other guys say that? So I wasn't, you know, I guess he was more of an engineer. So anyway, he understood the way I talked. So when all these technical questions came up, I would go to explain them. So he set up, one of the first things he wanted was a strategic planning team to say, what's our strategy for the 90s? What's important? So he pulled me onto that also as a corollary job. So it was, you know, about quarter time on that strategic planning team the last year. What was obvious in this team we pulled together to do strategic planning, they were all borrowed people from within the company, you know, generally high-level managers. It was, when you look at the drivers coming up for the 90s and beyond, power quality, et cetera, we weren't going to do anything more in nuclear. That became obvious. You know, we were going to do nothing. The recommendation was, well, in 2000, 2005, take another look. But we're not going to do anything until then. So then it was like, well, gee, obviously, I'm on the ground floor of a one-story building. So I wanted to go somewhere where we could build, working on new nuclear. I wanted to get back to that. So I actually got called by the folks at INL.
Idaho National Labs.
Yeah, Idaho National Lab, where they were working on the new production reactor.
That's right.
So I said, you know, could you come out and interview for a job on being in charge of the technology development for the new production reactor? And, you know, we're not the lead concept. The lead concept's heavy water out of Savannah, but we're a backup concept. And if we prove that we can do this, we'll be the lead because it's a better concept. It's safer. You know, it's a more intrinsically safe concept.
And what was the purpose of the new production reactor?
To make gold quantities of tritium, pure and simple. That was its that was its mission, make gold quantities of tritium. Remember the K and other reactors, but the last one operating was the K reactor, Savannah River. All it made at that point was tritium.
And this is for nuclear weapons?
Yeah. So plutonium lasts quite a while, in the nuclear weapons, but the tritium decays fairly rapidly.
After a couple of years, they have to swap it in with some
So you
fresh
have
stuff?
to refurbish it, the amplifiers, as you call them, every couple of years. And so as they were running out of tritium to without the K reactor running, it was like, well, we need a new production capability. So they had a goal quantity, and that's, of course, highly classified. But so we were designing a concept with gas reactors to make tritium, which everybody thought, you can't do that, or it won't work very well. So, but we proved it could. We did. So as technology development, we developed a target. We did radiation experiments. In 3 years, we did 27 different irradiation capsules. I can't say enough good about the people at I We did 3 major fuel qualification capsules in that 3 years. Accelerated the heck out of them in order to get that data in time to support the decision on should we go gas or heavy water.
And what is a capsule? Can you describe it to me?
That from the outside it might look like a fuel rod, but it's some sort of, stainless steel encased or otherwise, metallically encased, and you have these fuel elements inside it that you put into the advanced test reactor and irradiate it under very controlled conditions of temperature and fluence, and then pull it out and tear apart the capsule and look at the fuel.
And so the advanced test reactor was a reactor already operating at Idaho.
Yeah, it started operating in '67.
And that's used to test all sorts of things, from the Navy stuff to whatever.
Its mission for 30 years was nothing but Navy, really. So,
what it does is it allows you to have an environment where there's neutrons moving around.
Lots of neutrons.
And there aren't, except inside of a reactor, you can't find neutrons anywhere else in that quantity.
Yeah, not in that quantity. Yeah, that has like a 10 to the 15th flux. So it's a monster. There's no other test reactor like it.
And so you put your capsule in, and then all of a sudden you can test how your fuel or whatever material is that you put inside would behave as if it was in its own reactor.
Exactly. So we did all that. Then, once you make a tritium target, we could test that in there too and irradiate it and see, one, did tritium leak out of it, to stay in the target? There was a criterion for that, not to have more than so much leak out. Then you have to recover it so that you can say, well, I can, and the goal for recovering it was 99.9% of it's recovered back out of it when I want to recover it. Yeah. And we had 2 concepts for that we developed, and we tested those, and they both recovered 99.9% or above. Wow. So the key off-ramps for the technology we resolved within 3 years. And so we were heading for, if we do these off-ramps, potential off-ramps well, we're going to beat the heavy water, which we did. We're clearly the leading concept once we got our reports in on how this technology development went.
And the idea was that you would have less moderation. Is that why you would need a non-typical reactor environment?
Certainly better at making plutonium than a gas reactor would be,
And for the tritium, why not just have a tube that runs through the middle of a normal nuclear reactor and just pump some...
pump some stuff in.
Pump some stuff out continuously and then separate it.
Yeah. Well, you got to get it in and then you got to get it out. And there's no good way to do that in a traditional power reactor, which is all sealed up. But you can put targets in that are that look like fuel rods, and then take them out and reprocess them later.
Test reactor had this concept where you could solve your pressurized environment, but you could have a tube that
the HER can do that. Yeah, absolutely. I'm sorry, with the loops.
And there's no way to retrofit a
power
PWR
reactor?
and just have a special cap with a loop that goes in and out.
No.
Is that too crazy?
Yeah, and I don't think anybody owner of a PWR would let you try. So, I mean. In very small quantities, you, in principle, could do that with the flux mapping system, but that's gram type stuff. It's not kilogram type stuff.
Right.
And we certainly in the high kilogram for this. So originally, we were to have these reactors operating in 2000, the first one, for new production, if we passed the test. So. When the Soviets shut down their weapons complex, which they did pretty close to the same time we did, theirs was orderly. It was like, okay, we got this process line for separating plutonium at Chelyabinsk. Well, when they said, okay, well, we'll keep running and we'll stop feeding into the stuff into the pipes here, and we'll keep draining them out here until it's all out. And then we'll do, it'll be all purified and we'll have waste that we can deal with and all that. When we did it, it was the FBI showed up at the gate, right, in September, was it September of '89? And with all of these environmental violations that have been occurring at Rocky Flats, and they raided Rocky Flats. The only people who knew it were the security guards, because they figured they didn't want a gun battle between FBI and the security at Rocky Flats. And the Secretary of Energy and a couple of others, and they were sworn to secrecy. So they did all this work to make sure they could safely get into the Rocky Flats, and then they went swarming in and had search warrant for everything, and for all these environmental violations they've been doing, and shut the place down. So it stopped right where it was, right in the middle of...
Which ironically probably led to much worse environmental hazard problems.
Oh, absolutely.
Because they cut things at all the different stages of completion.
Exactly. It's all in the pipes, just
the FBI this authority
rotting away. And Rocky Flats never restarted a thing, so it was from that point on, they were done. And so it was rotting, the things were in intermediate stages, and it was just a mess. So, and it was pretty much the same everywhere. Savannah River was sort of the same. Their stuff is in tanks, not in a final state. The plutonium plant, finishing plant at Hanford, same thing. So the whole complex would just sort of stopped in its tracks, and everybody was afraid to do anything. So the cleanup of that. So anyway, where that was heading was, right after NPR, in '94, they had set up this project in Department of Energy on handling the weapons residues, and so Hank Dalton was brought in, reporting directly to Charlie Curtis, who was the undersecretary, and to head up this project of dealing with that. And it grew out of a recommendation from the Defense Nuclear Safety Board. It was recommendation 94-1, dealing with the weapons residues. And, there were 6 tons of plutonium in these various residues. And if you look at all of them, the nasty nuclides, it was 20 tons around the complex that need to be gotten rid of. So Hank Dalton asked Idaho, and he knew people there, and he knew some of the people that worked for me. And so we went out and said, well, how can we help you? And he says, well, we're going to get all this pushback from the labs. I want them all to be working together as a single project to figure out how to get rid of this stuff at Savannah River, Rocky Flats, Hanford, Los Alamos, Oak Ridge. Oak Ridge, their main thing was the U-233 issues. So anyway, we put together said, okay, well, we'll put together a team of experts, really good people, and consultants and people from these labs, and to drive a complex-wide plan for this, and we'll evaluate it technically and make sure it's doable. And we called this little effort the Plutonium Focus Area. Okay. So, and I was the manager of it. So, because I took over in '94 the systems engineering function within Idaho National Lab, which supports pretty much all projects with system engineering help. So we had people helping projects in national security and environmental management and all things. But this one I sort of personally handled, and because it was just too much fun. Yeah. So anyway, I really enjoyed it for 5 years. And the other time I was managing that resource org. So it was really good.
So tell me about how you ended up at Areva.
So somebody who had worked for me at the lab had started off with being Babcock and Wilcox in '68. And so he worked for me maybe 5 or 6 years out at the lab, and then went back east and went back to B&W again. So I was talking to him. He says, well, they're looking to hire for gas reactors. Really? He said, yeah, look at their website. So that was Framatome. So I looked up the website. So, okay, so I went to follow the prescribed procedure and attached a resume and submitted on the website.
Wow.
A couple of days later, I got a phone call to come out for an interview. So So, and it was halfway between New York and Florida. I says it couldn't be better, in terms of location. Because that's what we were looking for. Let's get halfway in between. So it was sort of ideal. It was back east. It was reasonably close to both set of relatives, and so we were happy to take it. And Areva was a lot of fun. So a year after I got there, I became the chief technology officer.
Well, that's a pretty high position. That's not bad for someone who just threw his resume on a website.
Yeah, I'd say so. Yeah, well, it was, I was the gas reactor guy for a year, and it was like all of their effort, and it just kept expanding, is going to EPR, their Gen 3 offering, and it was taking all the oxygen out of the room.
Yeah.
And but meanwhile, the customers in the U.S., we want good services, we want refueling support, we want steam generators that have long life, and we want fuel that doesn't leak, and so on. All of those things that require R&D and effort is still the bread and butter, always was the bread and butter at Framingham U.S. And I didn't do the R&D. Everybody else did R&D on their product lines, but I got to help orchestrate it. I got to help get the processes sort of sorted out and get it on a more reliable basis. And so I co-taught. We had we created a course between marketing and myself called Sales and Innovation, right? So so I would do the innovation part, and the marketing guy would do the sales part, and we co-taught that course that we created, and for several years, and so that was sort of fun. But I got to know all of who was really good at innovating in each of the product lines.
And so how did the company think about product lines? Was it divided up based on, let's look at all the various fuel and moderator and coolant combinations, or was there a favorite in the company and then it was about looking at different sizes? How do you think about the product?
Well, 95% of Framatome is on installed base. So, at the time, 104 units in the U.S. We also supported some units internationally, the Taiwan units, but so about 35 to 40% of the fuel in all the U.S. reactors comes from Framatome, right? Framatome makes it, even though the only original OEM plants in the U.S. are the B&W units, because Framatome had bought B&W back in the late 80s. So we were the OEM supplier for fuel for those, and still are. But for Westinghouse units, combustion engineering units, and even GE units, we became a pretty significant supplier to them. And so we're always bidding on every fuel bid. And always trying to innovate in fuel and try to make it better and more robust, better performing, more margin, that sort of thing. So that moves along very well in the U.S.
But these were all standard uranium dioxide in a fuel assembly. And so there's innovation
until
that
recently.
Can happen there.
Yeah.
And then, but what are some of the other more exotic fuel approaches that you guys might have looked at?
Well, fuel is a very slow part. I mean, if you make any reasonable size change in a fuel assembly, it's 10 years before you can get it to market. It just takes that long to qualify it, verify it.
Yeah.
Somebody's got to do a lead assembly test. You have to see how that goes, and then you can really market it in full. And you're going to have somebody going, well, I don't know, but maybe I'll take one reload and see how it goes. So it's probably 15 years before it achieves any real market penetration.
And that's for a change in fuel in a normal operating plant. So how do the new companies, the new approaches, if it takes 15 years just to make a change to fuel, how do they expect to get through the entire process for a whole reactor?
See these processes like say, but unlike all the U.S. fuel, we're not going to use uranium oxide. We're going to use uranium nitride. You go, yeah, sure, that'll cost you $1 billion in about 20 years, right? And then you may have enough data that a utility can say, okay, I'll use that instead, because it's just enormous, so we've pointed that out again and again at these small reactor meetings in the last 10 years. Say, you're looking at a $500 to $1 billion effort if you're coming up with something other than zircaloy UO2.
Yeah,
you just added $500 to $1 billion to your project.
And when you say zircon UO2, you mean the standard fuel assembly
Standard
that goes
type
in
fuel
every
assembly.
light water reactor
Exactly.
operating in the country.
Exactly.
And then, okay, but so then what's their pushback? Because a lot of these companies have been able to get some traction. They've been able to raise, 20 million here, 20 million there. And then what do they think that they have that they can get through the NRC faster than this 15, 20-year process?
They probably just don't know any better. So let's take NuScale. So NuScale is taking fuel from Framatome. We're providing their fuel.
Yep.
And it's the same envelope we've used, even some of our tests in the past. Rather than testing a full-length assembly, we would just cut it at half length. It'd be a standard assembly, but only 6 feet long. And that's exactly what NuScale uses, a 6 foot long fuel.
And does that work? Is that an easy process from a manufacturing perspective to just cut it in half?
Oh, yeah.
And could you cut it in 3/4? Is just as easy?
Yeah, it's just as easy, yeah.
And it's easy enough, does the software to model it work the same way?
It does.
Okay,
yeah.
so as long as it's the same standard configuration, you can vary the z-axis.
Yeah, the z-axis is no problem.
No problem,
right,
and then that's it.
But if the typical change that has required a long evolution is you say, I changed the grid, because the grid strap changes the flow characteristics around the grid and in the fuel assembly. Because I figured out how to get better flow or whatever. That takes a lot of years to change that grid. A lot of competitive advantage too. We went to the HTP grids in 1990, and it was a market beater for quite a while because nobody else figured out how to solve that problem of rod fretting and that sort of source of fuel failure. Debris filters at the bottom, things that'll filter out small wires and things that end up causing fuel failures. That really started at Framatome, so in the 80s. So, and they've really perfected that more since with better modeling tools, which have come along since 2000.
And have you gotten a chance, through your position there, did all the various startups or companies, given that they're the big company in the space, I would imagine, for instance, when I used to run my drone company, we approached all the large robotics companies to keep them in touch with what we were doing, potential acquisition opportunities. Did you get to see a whole range of smaller nuclear companies with different ideas come to you and pitch you guys?
No, they don't generally do that.
Why not?
Well, again, I think it's because, in 13 years ago, there were the cachet was small modular reactors. Mm-hmm. Everybody's saying, oh, that's the way to go. That'll solve all our problems, small modular reactors. And indeed, if you design them to be inherently safe, like NuScale is, you can walk away and the thing should be okay with nobody there in an accident. So it's designed to be inherently safe. But in general, when the early phases, what was the MIT one that was molten salt? Went belly up last year.
I know what you're talking about.
They've done a few physics calculations.
But we need innovation. We need people trying new things. We need people just going for it anyway. Right. But it does seem in nuclear that's very difficult to do because of all the school and qualification time. Yeah. Has anyone ever come to you and said, is there another way we can fast track this? The example I always like to use is, why isn't there some carve out in the rules where if you do something in the mine shaft, you can do whatever you want? Because it's a mile underground. Do whatever you want. We don't care. It's
that's what National Reactor Test Site used to be in the 50s and 60s.
And how come we can't do something
like
that?
And in principle, you still could. Yeah. Because the Department of Energy can self-license. They can prototype. If it's not going to be used for power production, it doesn't have to be an NRC license. In principle, they can still do that.
Yes, and then you'd have to go through the Department of Energy in that case.
Right,
yes.
Right. So they would have to be shepherding it somehow. And I think most advanced reactor concepts have approached Department of Energy labs about that, whether it be Oak Ridge or INL, but they generally have. Framatome approached 2 of the SMR vendors and saying, we think you've got a workable concept. We'd be happy to help you.
Great.
So one was NuScale, and the other was Empower with BMW. So both of them had said, oh, that would be great. What can you do? Let's talk about scope. And we said, well, the first thing you need is fuel. We'll take care of your fuel.
Okay, yeah.
Oh, sure, that sounds good. So even Empower agreed to that.
Yeah.
But then they went belly up a year later. So, they went, well, B&W Corporate BWXT pulled the funding from the project internally, said that, this is going to take too long, too much time and money, and we can't afford it.
That's a real shame. Are there other companies with similar approaches that say, hey, let's just make the standard thing smaller that might be popping up, maybe even around the world?
Well, I mean, the Korean smart reactor is just really a small little PWR. It's not integral like the NuScale was. The innovative, inherently safe ones were all integral. In other words, all the components are inside the reactor vessel. So pumps are inside it, and there's heat, steam. The steam generators are inside the vessel, and then the first thing that comes out is steam, and then penetrates out to the turbine. So by being integral, it creates a number of advantages that you can't have with a large stick-built facility of inherent safety, basically. You have a steam line breaker, who cares? You have a LOCA, so what? It's all inside the reactor. It's just leaking into itself, so who cares? That sort of thing that comes from having an integral PWR. And so that's why we liked the NuScale and the mPower. They had that. Some others, a lot of the SMRs were innovative to the point of not being practical in a variety of ways, and we evaluated them as we could offer to help, but we'd just be, prostitutes because we don't think it's going to work. But we thought those two could work. And we think gas reactors would work. If somebody wants to do anything with TRISO fuel, we think that'll probably work because it's a pretty well-known form now. And pretty robust and proven with the AGR program at Idaho. So there's 5 or 6 of the current advanced reactors that use TRISO.
And is it going to take them the same 10 years to get through fuel qualification?
Yeah, of course. Yeah.
Well, that's not what we want to hear.
So it depends. The fuel they're qualifying in the AGR program was from BWXT. So, I mean, it was all done there. It's kernel formation, the coatings, and the compacting were all done there. Some of that equipment has been moved out to Idaho, so it's no longer at BWXT. And I don't really know if BWXT just wants to get out of the business or what, or if Idaho just said, well, we paid for that equipment, so let us have it out here. But in general, is Idaho National Lab going to become a commercial fuel vendor? I don't know. So they can if it's for government purposes, but if it's for a commercial outfit, I think that's not very workable. So you're going to have to stand somebody up, whether it's BWXT again or somebody. X-Energy's trying to create a fuel capability. But listening to them talk about their fuel development effort, I think they're on the $500 million track to get to the same point that BWXT was. So it's going to be tough.
So Finis, as we wrap up here, maybe you can just give me kind of your outlook to the future. What do you think people should do, and where do you think nuclear could be in 10 to 15 years?
Yeah, well, here's what we should do.
Yeah.
Okay, because that's the important thing. I think before we turned the camera on, I pointed out there's no solution to climate change without nuclear.
Right.
Period.
Right.
I think socially we need to be building advanced reactors. Not that current reactors aren't safe; they are safe. They're the safest form of making electricity we have. Even better than wind. So, but from a social viewpoint, they're unacceptable because of their social impact when you have an accident. People are just too afraid of it. So if you make an intrinsically safe reactor, which has always been possible, it's just that we went down a different track. So if you make an intrinsically safe one, you say, well, I have an accident, so what? Tsunami hits it, so what? Tornado takes out everything, so what? Then you've got a different contract with the environment and with the society at large. If you then do that, now you can penetrate nuclear greatly. If we had 500 or 600 gigawatts of nuclear electricity or in process heat in the U.S., our greenhouse gas footprint would virtually disappear. And that's what we need to be doing. So now how do we get there? Like you say, you got these development challenge is, well, we need to be building prototypes. These 2-year paper studies that we do in series with the Department of Energy, and we do a dozen paper studies over a few years, leads you nowhere. I mean, it's the front end 1/10 of 1% of what it takes. You need to build prototypes. Now, it looks like they're going to help with building a prototype of NuScale at the lab. So at least going to help with the siting. I don't know if they'll help with the construction. But in my mind, if the government would do a significant cost share on prototypes, and at Idaho National Lab, how many prototypes were built of reactors from 1946 to 1962?
Something like 50 or something, right?
Yeah, exactly. There were, well, actually 62 of them.
Wow.
So 52 were on the INL site, 10 were elsewhere, but like the molten solid reactor, and that's at Oak Ridge and so on. But 62 different, and the government built them all, right? So, well, let's try this. And so they built it. Didn't necessarily follow through very much because it kept coming back to, well, the light water is already so far ahead, let's just do that. Well, we need something different. I think the advanced reactors have a number of different candidates. I would build a molten salt. I would build a sodium. I would build a gas reactor. I would build 4 or 5 of different concepts, and then have them ready for market. So now we can get out there and say, okay, well, we've proven this concept with this prototype out here. It's operating very well at Idaho National Lab. It's putting electricity on the grid, maybe not a lot, but some, and we can build these all over. So now you're miles ahead. Commercial industry won't buy them unless they're proven, and you can't prove them without a prototype. So that's what I think we need to do.
Finis Southworth, thank you so much.
Thank you, Bret.